So in this video we are going to solve a very interesting type of problem. It's asking that what should be the velocity of the particle when it is initially imparted with an initial velocity v0 which is perpendicular to the direction of x-axis. Here the x-axis is on the plane of the wedge. Okay, so yeah, it's asking that when it becomes parallel to the x-axis, what is the velocity of that particle? And obviously friction is present here, so the value of mu is tan alpha. It's on the wedge. So let's start. So on this particle, let me take another pen. On this particle, at this direction there will be force due to gravity, and it would be because of the component of gravity, which would be mg sine alpha. Alpha is this angle of the wedge. It is the inclination of the wedge. Okay, so that particle will also impart a force normal to the plane of the wedge, which is mg cos alpha, and due to this mg cos alpha it will experience a retarding force due to friction. Okay, so let me assume that at any general time it has a velocity with respect to time t. Okay, so at this point it will experience two accelerations also, which is due to frictional force, which is a retarding acceleration, and one is the gravitational force. Okay, so gravitational force will also have a component in the acceleration. So this question is interesting because it has an interesting kind of approach to solve this problem. So let's form the equation. If I assume this angle to be theta, this would also be theta, and this is the direction parallel to x-axis. So if I take the component of g sine alpha in this direction, in the direction in which it is moving at the instant t, it is let me assume that acceleration a net in this direction is a, and in this direction it's ax. Okay, so the value of a is g sine alpha cos theta minus mu g cos alpha. This is the value of a on the particle in this direction in which it is moving at that instant, and the value of ax is equal to g sine alpha minus the component of mu g cos alpha in the direction of x-axis, which would be mu g cos alpha cos theta. And we get an interesting result by solving these two equations. The value of a would be g sine alpha cos theta, and we'll put the value of mu in this equation. It will become 1 when we take g sine alpha common. Okay, and ax is equal to g sine alpha 1 minus cos theta. So yeah, here's the interesting fact that a is equal to minus of ax, which we can write in the way that a plus ax is equal to 0. So yeah, now we will start the integration. It will become dv plus dvx equal to 0. Let's integrate it. So what we get, it's the velocity of that particle, and it's the velocity of that particle, of the same particle, but in the direction of x-axis. So yeah, it's type of constraint relation when we do which we do in many problems. So yeah, initially the particle was having a velocity of v0, and we have to find at that instant. So let's assume it will become v, and in the direction of x-axis initially it was having an initial velocity 0, and after some time t it will become vx. We are just assuming now. Okay, so by integrating we'll get v, and by putting the limits finally we'll get v minus v0 plus vx equal to 0. So obviously from here we can get the value of vx, which is in the direction of x-axis. It will become v cos theta. Okay, so v minus v0 plus v cos theta equal to 0. So from here we get an interesting result, which is v is equal to v0 upon 1 plus cos theta. So this is really interesting. Okay, so now just it's the last step. when the particle will come parallel to the x-axis, this theta will tend to 0. Okay, when this theta tends to 0, we'll put the value of theta here 0, and it will become v0 by 1 plus 1, which will become v0 by 2. Okay, so yeah, that was the problem, and that's what it was asking. So yeah, okay, that's it. Thank you.